All right, well, welcome everyone to November's pickup meeting. And today we just thought we would share with everyone what we've been up to, what things you've tried during the semester, what seems to have worked well, what maybe you would like some advice or feedback on. And just to get us started, I'll say that this semester, when I did the falling sphere in my intro physics class, I did it in 2 dimensions. And so I really emphasized the fact that the resistive force goes opposite the direction of the velocity. And that seems to have gone really well. And I really liked the conceptual part of it because it was the first time that we, usually we just talk about vectors, but then we break up every problem into an X and a Y. And this was the first time where the students actually had to kind of think about the 2 dimensions together rather than splitting it into parts. So I think it went really well, and I'm going to keep it that way for future semesters. So opening up the floor, would anybody else like to tell us about what they've done?
I'll give a comment. So in my intro E&M course, one thing that I was happy with this semester is the students seem to become, I don't know if comfortable is the right thing, but they seem to want to and would make use of SymPy, which is Python's symbolic math library, to do integrals and solve systems of coupled equations. So that's something that I told them repeatedly is, okay, we're at this point, there's an integral to be done. You can do this by hand using the stuff from calculus, or you can use a computer. I don't care what way you do it. And the students became willing to do that on their own without me specifically telling them to. So I was happy with that.
Cool.
I tried to do something kind of like that when I'm teaching modern physics, and I tried to incorporate Mathematica into the course, although I don't think my students got to the point where they on their own would go off and say solve homework problems doing Mathematica unless I explicitly suggested this problem such that you want to do that. I think my students would probably need more practice first, or more higher level of comfort with it.
And I will say that at the same time that the students were taking this class, most of the students were also taking our sort of intro to computation that's taught in our department. And in that class, they became comfortable with the environment, just opening up the environment, doing things in the environment. So the things I introduced them to was the physics stuff, and specifically using that SymPy library. So I think that did have a lot to do with the fact that they were willing to do that on their own, because there was less of a barrier to overcome with being uncomfortable just opening up this thing.
What is your intro to comp class like?
So I've taught it lots of semesters, but I'm not teaching it this semester. But it is introductory, and in it, it's Python based, and they do physics and scientific computing problems. So data analysis, simulating things with the Euler algorithm, that kind of stuff.
Dave, I'm curious to know whether this was the first time that you tried integrating computation into that class, and what kinds of activities they were doing.
I did a pilot test of it over the summer when I just had 4 students in a summer course. And with those 4 students, I felt it worked better perhaps because with 20 students, I feel like I'm rushing around everyone, as some emergency because they're not familiar with Mathematica or whatever it is. But it seemed to work well over the summer. The activities I had them do were a lot of graphing. So for example, with wave functions, you can look at different energy levels and maybe have Mathematica show what is the most probable value for some observable with different quantum numbers of the wave function and so forth. So it was a lot of visualization and a little bit of integration.
Nice.
Larry, can I ask what you think of SymPy? Because I introduced it in my computational physics class just as, I think, like one day I showed them how to use it, and I said that, they can use it if they would like, and didn't really follow through with it. So I haven't used it a lot, but from what I saw, it looks like it
Hello.
can do a lot of what you need it to do, but it's not as if you actually wanted to do symbolic calculus, like Mathematica is the way to go. So what did you think?
I think it's for the things that you are done in undergraduate physics. I think it's perfectly good. I think Mathematica is sure to beat it when you come to doing very fancy math stuff. But in terms of its mathematical capabilities, I think it's not lacking in any way that I would care about. And when used inside of a Jupyter Notebook, you get the pretty output of things. And so I'm happy with it. And I think it's simple enough in terms of syntax that students don't find that to be off-putting.
Thank you.
Yeah.
Good. Would somebody else like to share what they've tried this semester?
All right. Sure. So for me, it was the first time using Jupyter Notebooks. I'm coordinating the University Physics 1 lab course. So that's 4 sections with up to 24 students each. They are taught not by me, but by our grad students. And so what I did was I added some computational components to 3 out of 13 labs. Actually, 1 lab was entirely focused on computation. That was about measurement error, statistics, and then I added a computational component to 2 other labs. One is free fall with air drag, where we have the students drop cupcake liners, 1, 2, 3, 4, 5 stack liners, and they use Logger Pro to record the video, they analyze the video, and then as an additional activity, I had them integrate the equations of motion. And then the last activity was analysis of simple pendular motion. So with computational physics, you can see what happens if you go beyond the small angle approximation, go to initial angles of 45, 50, 60, 70, 80 degrees. And then after those 3 computational labs, I did a survey, and about half of the students in the lab actually responded, and a lot of them hated it.
Oh no! Did they give particular reasons why? Did it find?
Well, it was interesting. So one answer was, get rid of it. With no previous coding experience and no crash course in it, makes the entire lab more challenging than it has to be. Someone said something like, I'm not a physics major and half the class are not. We don't ever need computation. The interesting thing, though, is that half the class are engineering majors.
Oh, that'll work.
So perhaps,
Little do they know.
yeah, perhaps trying a little bit more scaffolding and a little bit more being upfront with the why.
I think so, and we definitely have to work on students' expectation. One thing I can do, if anyone is interested, I can share the Jupyter notebooks that I was using. Let me see if I can copy. Let me see if that shows up as a clickable link in the chat. Not sure. Let's give it a try.
Yep, I see a lot of links.
Yep. Mm-hmm.
Do you plan to put them on PICUP?
I'll have to see. I might, although I think many of them are very similar to stuff that's already there. Okay, so for example, the free fall is something that I actually partly adapted from Kelly's Jupyter notebook, and I think pendulum is also there.
Yeah. This is great, Axel. I just clicked on the last one. I would encourage you to at least post it on Slack so that it's there as a permanent
Okay.
message. And then, I think, we'd have to look through in a little bit more detail and see if
Sure.
Either add them as variations on an exercise set or as a new exercise set. Maybe Larry can.
So these are all complete. Did you have any code that's there provided for them when they started these assignments?
So these what I posted are the instructor versions. So there are a number of activities, exercises in there that the students have to do. So the first thing I have to have them do is simply add some comments to existing code. And then the next thing is they copy some existing code, how to generate a plot, how to generate a histogram, for example. So they don't have to do they don't have to write code from scratch. It's mostly just copying and slightly modifying existing code.
Nice, very nice. Thank you for sharing, Axel.
Sure.
Do we have other volunteers?
So I just want to say I'm sorry. I'm usually really chatty, but I'm teaching a computer science class this semester. So I do a lot of coding, obviously. That's the purpose, but it's a little bit different. So I'm more listening.
Give us a highlight.
A highlight of the class?
Yeah, like something that blew you away that the students did, or something that you thought was really well.
I thought was super cool is, so I even when I was doing computation for my PhD, it was computational science. So we did some really cool assignments, like we did a Twitter sentiment analysis, and we also did a network analysis. So find the most central person in a certain network. And so we did one with Paul Revere and that sort of thing. And I just thought it was really cool how they're using the same methods that we're using in physics classes. I mean, they don't really have differential equations in that class, but they still have, a lot of linear algebra and that sort of thing, but applied to things that I think are really catchy for non-scientists. So it was fun to see those applications.
Yeah, nice.
I have a question or comment for those of you who use scientific programming in your introductory courses. I suspect a lot of you are using matter and interactions or something similar. So a lot of my computational assignments in my introductory physics course this semester involve momentum updating and then position updating in the usual way, like using a modified Euler algorithm. And I think students had maybe 5 or 6 assignments in class or in lab where they did that. And I didn't get the sense that students really knew better on the last time than the first time. Like if I tell them, I give them a comment that says, okay, this is where in the code you're going to update the momentum. This is where in the code you're going to update the position. And I still felt that students didn't remember, first of all, that update means you take the old value and use it to calculate a new value. And secondly, that they knew what to do with it. So I would have thought that after seeing it 6 times doing the same thing, that they would have some recollection, but it seemed like they just sort of every time just got stuck. What do we do? How do we update momentum? And they would just start guessing.
Put it in an exam.
I was tempted to have a lab exam or something where
that's what I do, because I find that students, I mean, the engaged students will pay attention and want to understand no matter what. But for the students that really are in the class, wanting to get something from it, but mostly just to get a good grade and move on, they're not so much paying attention to the whys and the hows. They're just trying to get through. But knowing that it's going to be on the exam prompts them to look into it a little bit more and make sure that they understand what's happening. And so for all of the labs, I have a little exam component so that they see that, this is important. You should understand how this works. And if you don't, then you should ask questions. It shouldn't just be, because my partner said so, I put it in here and got the lab completed.
So when you say all of your labs have an exam component, do you mean each lab individually or all your lab courses?
all of my courses where I do computation, and in particular, I was thinking about my modern physics course where I actually have time to do lab exams. But anytime I introduce computation, I have something on the exam that relates back. And it can be, even something really simple like giving them a little bit of piece of code and asking them, what does this do? Or maybe writing, like with what you were saying, you could have them write a little bit of pseudocode with how you would update things. In the lab exams, I actually have them code as part of the exam. But
I would be happy if my students could, given a force, update momentum of position and also understand where those equations come from, relating them to Newton's second law.
That's a big step.
Well, I have something that I'd like to get some feedback on, if that's okay.
Sure.
So I'm teaching a sophomore level, Python lab course for physics majors this semester for the first time. The course is new and it's going to be taught every semester from now on. And for the final project, I kind of settled on a format that I feel kind of pleased with, but I'd like to know how to make it better if possible. So what I did was I created a list of competencies that I wanted students to show with their final project that they could do these various things. And I said, you can write 1 to 3 programs that include your competencies. And, if you can do this many, then you get a C. And if you can do this many, you get a B, and this many, and an A. And I guess I felt good about that because if it's I want it to be a creative effort, but I've struggled with how to evaluate creative products.
Mm-hmm.
So, it's maybe a little bit artificial, but I'm like, go ahead and make your program do this extra gratuitous thing just so that you can show me that you know how to do it. And then I've also give them a list of scenarios or problems out of Newman's book, just to say, here are the pre-approved problems, and however you want to go about this so that you can cover your competencies, then go for it.
And are they currently in the process of working on this?
Yeah, they're starting to sort of conceive how they're going to do this. Yeah, so one weakness that I can possibly foresee, it might happen, it might obtain, is that the trick is to get all these things working together, right? It's not to do all the little parts, right? Use a for loop, right? But it's to use a for loop strategically, in a way that actually advances you towards your objective. And so I don't have a way to evaluate that right now. I don't see how I'm going to do that.
Is using for loops a competency, or I guess I was thinking on a
It's 1 out of 50.
But I guess I was thinking like Euler's method, or something more mathematical. So they're specific programming tasks that they should be able to do. Is that how it's broken up?
Yeah, I've got other things like that. Edit data for a VPython shape in a while loop, for an animation. So it's not saying exactly what, it's not saying that you have to have any physics statement in particular. One of the competencies is write a statement that, that expresses a law of physics. So I don't know. It is a shot. It's a
What kinds of problems are they doing, Hunter?
Well, so I said, model the electric field due to a finite length uniformly charged rod, or illustrate the effect of quadratic air resistance on a particle moving in at least 2 dimensions, or things from Newman. Newman's book?
I don't. Well,
Okay, so there's like there's like a binary search thing. Well, I mean, or it doesn't have to be a binary search, but where you're searching for a solution to a 5th order polynomial, or building a sodium chloride lattice, or trying to remember what else there is.
Okay.
Yeah.
Because I think, as Michelle was also saying, that there's different ways of looking at competencies. The way I've structured my labs is they have a problem, and if they get to so much of the problem, then that's a C. And if in addition they do, so I have them do this one lab where they have to model a 2-step system, and so there's this particle bouncing around and it can go up and down this step. And so if they can get that working, that's a C. If in addition they can take data for different heights and plot it in a way that makes sense, that's a B. If in addition they can extract parameters from the data, then that's an A. So it's not so much looking at individual coding things, but at how much of a problem they can actually complete.
That makes sense. And that reminds me of Aaron Titus's
yes,
frameworks that he uses.
very much like that.
And I think for a situation where I'm specifying the problem, that makes sense.
Mm-hmm.
For a final project, I thought it'd be better to do something more open-ended.
So I'll say that I use Newman's book for my computational physics class. We work all the way through it, and then they have a final project at the end that they write a proposal for, and they get feedback, and then they have their first code submission, get feedback, and then their final code submission, and then they do a presentation as well. But I also struggle with that final project on assessment, since everyone has chosen good projects by the end because they're receiving feedback along the way, but then they're also different. That's something that I struggle with, so I don't have a solution, but I think it's maybe along the lines of the same problem.
Yeah, right.
I think it's an interesting question that you had at the beginning, Hunter, of if you list out all of those competencies, and you said about 50, what that list should consist of in general.
Right. Yeah, I don't know.
I don't think it's a question that has been answered, or that necessarily everyone would agree on.
Yeah. Well, and also, I mean, I'm feeling the tension, I'm not hating it. It's fine. Between students who, have done 0 with computers, with computer programs before this semester, and others who have, taken a course in C++ or something. So I'm really trying to, I'm kind of aiming at those, because this is a required course for physics majors and minors, and it's designed, I see the course as being remedial in a way, that it's meant to get everybody up above a certain minimum level of ability, so that they can go into their upper division courses and they can be assigned this or that, particular problem by those instructors and be reasonably expected to do that. So
Larry, I don't know that this addresses the exact same kind of skills, but I just pulled out the AAPT guidelines for, what is it called? Recommendations for computational physics. And they do have a table that lists kind of competencies that physics majors should have. Of course, this is at the end of their undergrad, not at the sophomore level.
But does that, I don't recall, I don't think that breaks down
It does. So it has things like students should be able to produce static visualizations of data. Students should be able to query databases effectively for information. Let's see.
Those are bigger picture kind of.
Yeah, those are kind of bigger picture, but maybe it would help a little bit with the assessment in that you're not necessarily saying you have to have, you know, a for loop, an if statement, etc. But, you know, rather bigger picture. So if a problem, right, if a problem is better attacked one way than another, you're not losing points because you're not putting that computational syntax or whatever that's called in. It's more, were you able to solve the problem? So anyway, might be.
Yeah, Mari, I agree with you. It's the way I've set it up makes it possibly a little forced. But also I told them to do 1 to 3 programs to sort of show all the things that they can do. And so maybe, you know, this is not appropriate for this problem, but it's appropriate for another problem, or anyway.
I think that sounds interesting and doable.
Yeah.
I don't know what the students, you know, might think, but
yeah, I don't know either.
Yeah, good. Well, maybe we can have another update from you after the semester.
Yeah. So I just want to say thanks for pointing out the AAPT guidelines thing, and it's something that we should definitely think about for our program as a whole.
Mm-hmm. Sure. Let's see, anybody else want to jump in and tell us about their course or ask questions?
I guess I can say something about SymPy. Question that was talked about earlier. Right, this semester I'm teaching a standalone computational physics course, and I think, like Michelle, I also kind of briefly told students about SymPy, but some really took and ran with it, and they did things that I myself wasn't aware that you could do. So I think Larry pointed out that it seems like you could do a lot of stuff. Some, for example, try to even solve inequalities, non-trivial inequalities with SymPy. So one student, I think she's really expert in, she dug very deep into it. So I actually made a group, Google group for the class, so they could post their tips and tricks and whatnot. And so it's very useful. It's more useful than I thought they would find. In particular, I think, I'm not sure your experience, but the average student in my class, they are not the strongest in terms of analytic proofs. And SymPy seems to really help them a lot.
Yeah, and actually the things that I have used it for, had students use it for, or actually let the students know they could use it for, is doing symbolic calculus, integrating, differentiating, and solving systems of equations. That's pretty much it in terms of what I've told students. Here's this tool you can use.
How does this compare to, say, Mathematica or Wolfram Alpha? I would have thought that Wolfram Alpha is web-based, and so people can just type things in, even with spelling mistakes or missing backups, and you'd still be able to do integrals. So, okay, let's see.
Yeah, that's a good question about Wolfram Alpha. I mean, in terms of Mathematica, I'd say the two differences, one is cost, that if you don't have a Mathematica license, they can use it. And the other is just what they're already using. And whatever thing they're already using, this provides them the opportunity to use it in Python if they're using Python. But yeah, I'm not sure how it compares to Wolfram Alpha. And you're right, Wolfram Alpha is free, right? I don't know if others have had experience that can compare those.
Well, I think Mathematica or the Wolfram Alpha, they seem to be more powerful. But for SymPy, I like this in the within the Python family of Python environment. So they could do this in Jupyter Notebook. They could do it, on terminal commands, and so I think there's just better integration. But for some, I think dedicated, tasks, probably Mathematica is better than SymPy.
Wolfram Alpha, you can only do one thing at a time. Is that right?
I think so.
So you can put in an integral or you can put in a plot, but you can't really do kind of 3 rows of thing or 3 different things. So it's really good. I use it a lot for integrals just because you can put in an integral and do it. But I think if you wanted to integrate and then maybe plot the function, then it starts getting a little bit more cumbersome.
It also limits the amount of computer time you can use at a time. So for something very complex, it sometimes tells you you've run out of time and you don't know it's going to run out until it already has.
Yeah, well, I guess I haven't tried complex things.
Yeah.
Good to know, though.
For me, I was wondering, not because I thought it would be like an equal to Mathematica or Wolfram Alpha, but if they're learning Python in computational physics and they learn symbolic Python, like, is it sufficient, or are they going to have to go into an upper level class and use and learn Mathematica, which we just spent time learning how to do the same thing in a different language? Like, is it worth it to teach SymPy? Was kind of where I was going, but I guess it totally depends on your, like, what you're trying to do with the tool.
Yeah, if I can comment on this, some students figured out that you could use, say, an analytic expression from SymPy, and then use a function called lambda phi. So that becomes a regular function you can call from your Python code. So I didn't know that was possible, but turned out to be a pretty nifty feature.
Okay. Well, I'm curious now. We have 12 participants. How many of you were using Python in your courses? Maybe just raise your hand. I'll count. Okay, all of the ones in the current screen. And everyone but 1 and 2 people that don't have video. Oh, there comes Deva. She raised her hand. So let's see.
I used to.
And you, Jay, you use it too. Okay. So maybe everybody but 1. So I guess that's the thing.
So who is that, and what are you using?
Are you talking about me? Well, so in my Physics 402 class, I use Mathematica. Well, mainly because you have the capability of doing symbolic algebra, numerical mathematics, and plotting, which of course you can also do in Python with matplotlib and things like that. It just happens to be what I use for my research as well, so there's some synergy there. Well, yeah.
Yeah. I've been using VPython in my intro class, but I typically use MATLAB in my sophomore modern physics class just because there's a lot of engineers in it. And I do think there's a lot of value also in students seeing different packages, right? So that by the end of their undergrad, they've done MATLAB and Mathematica and Python and LabVIEW and whatever else you can throw at them.
It can be difficult if, unless it's within the context of a course. So I was going to ask how people feel about trying to embed computation in ordinary courses versus just having dedicated courses. So, what was I going to say? For example, I'm teaching on University Physics 1 here at the University of North Dakota. And students have so many problems coming in. We lose 1/3 of the students anyway. even without trying to do anything funny.
Mm-hmm.
And they grapple with units. They don't realize that you need to write the left-hand sides of equations before starting a working. They don't understand the meaning of the equal sign. You will have people doing something equals something and then multiply by 2 equals something else. So it seems that all those habits that we need to fix and to just teach them the language and how to think. So I did take some baby steps, including the screen sharing work here. Can I try screen share?
Sure.
Let's see. Oh, how does it work? Desktop? No.
I think if you...
This.
Yes.
Does that work?
That worked.
Yeah, so this I did just yesterday, in fact. It took about 30 minutes after class to get the students to fill out the table for basically Euler's method, or what you call the modified Euler method, I think, for calculating the motion of a projectile, or rather an object in free fall.
Mm-hmm.
And then on the next page, the same thing with a mass on a spring. Do you see my cursor?
Yep.
Yeah, so if they do this correctly, it's all actually integer algebra because I chose 1 for all the constants. And they end up getting oscillations going from 1, 0, -1, -1, 0 to +1 and repeating again. So that's something that's possible to do by hand without too much tedious calculator work. And I was actually quite pleased that I think I walked around the class to see how they were progressing, and I think they all did very well. Maybe a couple of people got confused about which numbers to combine. But we sorted out pretty quickly, and they got the graphs. So what I didn't get to do was to run some kind of assessment or even a survey to ask, did you enjoy or appreciate that activity? So, at least Axel managed to get feedback.
Mm-hmm.
Yeah, so I'd be interested to hear, how do you decide whether to do this again, to go further or to stop doing it?
I have a question for you. Was this entirely on paper, or did you have them also do this in a spreadsheet?
This was entirely on paper.
Okay. I think this kind of thing would serve as a nice opportunity to then show the power of a spreadsheet even without doing it in a programming language. That you do something repeatedly over and over and over again, and then you can show them that, hey, you can magically fill in all of these once you've done it on a given line. But I think that looked very nice.
I tried for the first time using Excel to do that. Normally I only use Excel for plots and data analysis, but inspired by some of Rooster's items on PICUP, I had them do position updating in Excel. And one challenge of that is you then have to deal with Excel's obscure ways of referring to other cells, like D6, instead of referring to
you can name them now, as I found out not too long ago.
Can you say that again?
You can name cells now, and so that
I think I did. I mean, I did have, or to some extent, I had a control panel where I said, okay, this constant has a name, and
yeah.
So I perhaps didn't implement that as fully as I could have. But in the end, I wasn't sure that it was really less obscure doing it that way than it would have been just to use my usual Python and GlowScript method. So for the rest of the semester, I used Python. But to get at the original question, I've been giving my students a survey at the end of the first semester. So after they've had maybe 2 labs that uses this and maybe 6 recitation sections where we do programming. And I haven't looked at this semester surveys yet because grades aren't in yet. So I was going to submit grades and then do it. But last year, I found out that from the written survey that the students find homework very frustrating if it involves any kind of coding because they don't have the skills needed to debug it. And so they can spend hours just getting bogged down in trying to do something very simple. And if they had 5 minutes with a TA or an instructor, they could get past that. So based on that student feedback, I eliminated all the homework from the courses. So it might be useful to ask the students, what is the most frustrating thing? What is the most helpful thing? And I found it useful.
I see, thanks. So do a survey. Okay.
Yeah. One thing I also wanted to mention when you talked about the equal sign, I'll have to look it up look it up and I'll post it on Slack, but there was a really interesting article I found a while ago about why the equal sign is so confusing, and it has to do with the fact that we use it in many different ways. Sometimes we use it to define something, sometimes we use it to imply causation, right? And so this article just listed all of the different ways that we use the equal sign, and how for people that are experienced, you know what you mean when you say equals, but for somebody who's starting out, it can be really confusing that we're using the equal signs in so many different ways. So I found it helpful to then be able to explain to students, oh, this equal means we're using it this way, and this equal means we're using it this other way. So I'll try to find it and post it.
I think their lack of understanding is much more rudimentary than even that.
My department's trying something that may be a bit wacky. We just did program review, and we decided we wanted to create a math methods course, but I think it's going to be a combination of math methods and computational methods, because we're going to try to integrate Mathematica. So this is, we designed it so that they would take it at the same time they're taking University Physics 2, which is second semester either of their first year or second year. And so they'd be taking it concurrently with their second physics course. And that does limit how much math we can do, because they won't have had differential equations or even necessarily vector calc. But we were hoping that giving them some Mathematica experience early on, then when we're teaching classical mechanics or modern physics or quantum mechanics, that we know that they'll have had some Mathematica experience and also get some mathematical methods along the way. But to do that, we had to sacrifice our second semester of classical mechanics. So we pay a price for that, but we'll see how that goes. We haven't tried it yet.
Is this starting this year or next year?
Yeah.
Okay.
I think it could be pretty useful. But the trouble with trying to teach anything is we want to think about it as a linear system where students go through this course and then this course and then the next course. But really, to get good at this, you have to layer it. So, for example, we are doing University Physics 1 from Survey and Jewett. So we do uniformly accelerated motion. And then there's a bit of a chapter where they talk about damped motion, and they say, you don't know how to solve differential equations. So we'll guess the solution, and we'll check that it works. And then you have a mass on the spring, and we say, you don't know how to solve differential equations. So here's the answer, check that it works. And I said, if you guys are getting frustrated with that approach, at least know that there is something called numerical methods. And probably a good idea to have a course on that. Having that together with math methods would be excellent.
Our math department offers a course in numerical analysis, which I think does like shooting methods and equation solving methods and stuff like that. And quite a few of our physics majors take it because it can satisfy the elective for either a math major or math minor.
I think it also sounds like a really great idea to put them together, because when I teach computational physics, so students may or may not have had math methods before, or they're taking it concurrently. So so they haven't learned how to solve PDEs or ODEs yet. I teach them how to solve them on a computer. And then I say, you're going to love Rangakata whenever you learn how to solve this by hand, because it's so easy. But, if they're in a class where they're learning it, then they're like, oh, I know what you're talking about. And otherwise, they just have to trust me, because I'm like, I'm not going to teach you this because you will learn this elsewhere. So it's, a waste of time, or it's redundant. But putting those together then kind of makes sure everyone's learning all that at the same time. And it's correlated.
We haven't heard from Todd or Saruj, is that right?
Saruj,
yeah, that's
wasn't
right.
working.
Yeah, I'm actually working now.
Oh.
Yeah,
good.
it wasn't I don't know if it was a mic, but it was certainly audio. I wasn't getting any sound. I switched computers, so Yeah, I missed quite a bit at the beginning. I could see you, but I couldn't hear you. But so I'm sure you were talking about lots of very interesting things. Yeah, so I can add. So typically, I teach. This semester would be the semester I would teach our computational physics course. It's a sophomore course. We call it scientific programming, and it's taken by all physics majors. And we in fall of their sophomore year. This semester, I'm not teaching it. Someone else is teaching it. They gave me. I kind of requested it an upper level thermodynamics, so it was since the pickup meeting that I came to 2 summers ago that this was my first chance to introduce some programming element in an upper level course. And so I gave one assignment that involved some coding. It was a spin-a-half paramagnetic system, and I wrote the notes for it and some code, just the start of the code for the solution using Jupyter Notebook. And so what they had to do was for a spin-a-half system with n particles, determine magnetization, internal energy, entropy, and from that come up with determine a temperature. And they were supposed to graph each quantity as they calculated it, and then they were supposed to generate a table. So all of the quantities were generated as Python lists, were calculated using Python lists, and in the end they generated a table with all of the quantities. And I had some mistakes in the deliberate mistakes in the Python notebook that I gave them to use. And the first question I got from it was do they have to use Python? Because some of them had never used Python before. So the students who took computational physics last year got an introduction to Jupyter Notebook. We teach in C, and so but I introduced Python and Jupyter Notebooks at the end of the last computational physics course. So the upper level physics students who took computational physics 2 years ago or 3 years ago, some of them, or even before that, they had not seen Python, and so I gave them the option of doing it in using something else, which was good for them. But the issue came when it came to grading, because I got less than 50% of about 26 students used Python. I got it turned in Excel, which I can't figure out as yet. I had Mathematica. I had Origin Labs. I don't know if you're familiar with this Origin Labs software. Anyone has used that? Yeah, so I have some of those, which took me forever to figure out how to open. And I'm still marking the assignment, and it's been about 3 weeks now. I think in a year, 2 years from now, when the course comes around again, we would have all the students would have seen Python in computational physics. And if I teach the course again, I wouldn't give them the option of doing it, choosing their language or platform. But it was a fun thing for them to do, because they actually got to calculate some of these state variables for a complicated system that they could visualize, but they're very difficult to do calculations by hand.
Are you using Dan Schroeder's book?
Yeah.
Okay.
Yep. So that table in the book, I had them go through and calculate the quantities and fill in a few more columns. Yeah, it's the first time. I didn't know about this book before I taught the course. It's a book that was used that they've been using here for a while at River Falls, and so I just adopted it because we have a tech. Students don't purchase textbook; they rent the textbooks from the university. It's actually included in their tuition fee, so I have to stick with the book. So that's what I did with that. But the computational physics. So typically we teach this course in fall. There's been a lot of demand for it over the past few years, and so now we have a section in spring. So we're doing computational physics each semester now. That's my update.
Great. Well, thank you.
So my experience with implementing computation this term has not been very successful. In fact, kind of a case study in how not to implement computation. Basically, I decided that I'm teaching applied optics and photonics, and I decided I wanted to revamp the curriculum and put a lot more computational activities in there. And so making two sets of changes at the same time while trying to deal with a 8-month-old has proven to be a little bit more taxing. And so I'm, creating the lecture material, I'm creating activities, and then trying to create computational activities. And what's happened is I just ran out of time to create more computational activities. And so I kind of stopped doing it halfway through. So when I had the activities, they were working really pretty well. And I hope to post a couple to the PICUP website. But yeah, that's, one of the messages to share to people is when you're implementing these computations, don't try to make any other changes at the same time. Just focus on one thing. So that's kind of where I am. And so at least, when I teach this course again in 2 years, I'll have, the first third of a semester of computational activities, and I'll have all the other curriculum materials. So hopefully next time around, it'll be a little bit more successful. So yeah, that's where I've been.
How big is the class, and do you know how they felt about stuff?
It's pretty small. There are 6 students in there, and they would actually like more computational activities. They've even said that they wish that there was more there. I've been using Sage Math, and in particular the CoCalc for the online classroom features. But they like it, and they'd like more of it, so that's good at least. That's all I've got.
Thanks, Todd. I like your advice. So a little bit at a time so we can keep our lives manageable. All right. Well, we have a few minutes left. Should we take a couple of stabs at next semester? Does anybody have anything interesting that they're planning, revamping their whole course, including their computational activities?
That's a nice.
Yeah, actually, I'm doing it again next semester too. Now that I think about it, we're going to be offering advanced lab for the first time, and I want to put computational activities in there. In part because the way we're trying to work with Alpha to try to develop some computational activities that combine the experimental and computational aspects. So that's kind of my goal, is to try to put some Python modeling in there with some of the experiments that I'm also putting together. So I really haven't learned my lesson, but my delusion is that over break, I will have enough time to actually do these things. I realize that's not realistic, but we'll see.
It'll be exciting one way or another.
Yes, I'm sure it will be.
Yeah,
I'm planning on revamping the second semester algebra-based physics lab, and I'm currently talking with people in our department and the college, figuring out like what is a lab according to them, and what can I get rid of? Like, do we have to have lab reports? Do we have to have lab reports every week? so like that's where I predominantly introduced computation into the intro level classes. I never have them do it on their own. I always have them do it in pairs together in class when I'm there, so that it's more about, you know, learning more about the physics material than like stressing about coding. And but of course that's a time constraint, so trying to find ways to successfully do a actual lab in addition to implementing computation. And so I'm trying to just rethink what goes on in those 3 hours that we have, and what people in the department in college will let me do and still call it a lab.
Actually, Michelle, I wanted to mention something to you. Kelly and Walter and I were at Northwestern last week doing a PICUP workshop. And one question that came up is there anything in computation similar to peer instruction? And so I mentioned the pair programming that you've been doing. And so there is some interest out there for that. That might be something that you could put together as a project and publish out there. I think there'd be some interest in people knowing what you're doing and how it works.
Oh, that's really interesting, actually. So you know, a lot of my pair programming methods I take from computer science education and just apply it in the physics classroom with a different goal often in why they're doing computation. But recently I have, I guess, unknowingly brought physics pedagogy into the computer science classroom. And so recently people were like, what are they doing in there with whiteboards? And we do the pair programming, but that's not new to them. So I guess I kind of made a hybrid pedagogy that I should maybe disseminate somehow.
I'm missing something. Pair programming, you said. What is that?
Pair programming is two peers, two classmates on one computer, working on one program or task together at the same time. So in computer science classes, here, and that's like the common pedagogy, is even all of their homework is done that way. In-class work is done that way. So and also in industry, some companies have implemented pair programming in the workplace, where there's one computer and two people, and the idea is that you switch off who's driving and who's helping, and they see better learning and better productivity that way, which is really fascinating. I actually think I kind of pushed back on it at first, and even if you look back on Slack, I think someone else had implemented in their computational physics class before I did, and I asked a million questions because it just, I don't know, it didn't seem like what I wanted to do, but then it actually is working quite well. And so in class, I actually time them, and I have this Python script because they're learning Python. So then at some point we go through it, but he'll say switch roles, and then they the driver switches. Homeworks, it's a little different, but in physics, I only do it for in-class stuff, the pair programming.
Interesting.
You said this is going to be done in an algebra-based physics lab?
Yes, I have not taught algebra-based physics yet, so we'll see if it's as well received as it was in the calc-based class.
Yeah, I'd be very interested to hear about it. The anecdote I always like to tell is, so a few years ago when we introduced video analysis to both the college and the university physics labs, I happened to be in the class when the TA said, okay, today we're going to do the last of our video analysis experiments. That was in the college physics lab, and the whole class went, yay. And that wasn't too encouraging. So then I asked a TA in the similar university physics lab to make the same announcement. This will be today the last video analysis lab. And the whole class went, oh. And I repeated that same experiment a year later, same result.
So I think I'm going to have a little bit biased results because over half of my class last semester I've had in either a computer science course or calc-based first semester physics. So they know what they're getting into if they have me as a professor, because I always make them compute. But if I go into like a first semester class, it might be different, very different.
Great. Well, it seems that we've come to the end of our time. So I'd like to thank everybody for joining us today, and we hope to see you again soon. And Michelle, you should definitely tell us more about that, because I think many people would be interested in hearing more about pair programming and how to do it in the physics classroom.
I actually took pictures one day of like things in the classroom, thinking that I would show it to you guys at some point, but I never did. So I think I'm actually prepared.
Yeah, post them on Slack, or maybe we could have an entire online meeting devoted to something like that. So, you know, it could be just that, or it could be something like different pedagogies. I can't speak English. You know what I mean. Different ways of teaching in physics that maybe everybody could share something. So great. Well, thanks everyone. I will stop the recording, and I hope to see you all soon.
Good night.
Thank you.